8 training examples. We gave exactly 8 examples to 2 separate models to see how they would learn. This chart maps the first outcome. A 1.5 billion parameter model rides an 8-example signal for 300 update steps, pushing its Math 500 score to 67%. But a 3 billion parameter baseline, on the exact same examples, hits a wall at step 55 and starts memorizing. The reward optimization is identical. The training recipe is identical, yet the learning outcomes completely diverge. That gap, the distance between a climbing reward score and actual cognitive progress, is the central problem of reinforcement learning from verifiable rewards when operating under weak supervision. I'm the bearded AI guy. The structural framing for this analysis comes from the human architects research briefs, which make these deep dives possible. Today, we are dissecting a paper by Salman Rahman and co-authors. Its timing is critical. Every major AI lab is currently betting millions of dollars of compute on scaling reinforcement learning from verifiable rewards, or RLVR. The authors do not conclude that RLVR is broken. Instead, they demand a strict, surgical reframing of how we measure its success. Their thesis is specific. Generalization is dictated by saturation dynamics. When models fail to generalize, the root cause is unfaithful reasoning, not lacking output diversity. We know that massive pretraining scale RL works. DeepSeek R1 and Grok 4 achieved high-level reasoning by leveraging expansive, mathematically verifiable datasets. But real-world deployment looks entirely different. Most production environments are starved for clean data, forcing engineering teams to operate under weak supervision. These columns illustrate 3 constraints. First, datasets are tiny because human labels are expensive. Second, the available labels are noisy and contradictory. Finally, without a ground truth verifier to check the math, engineering teams are forced to invent self-referential proxy rewards. These 3 constraints define the actual production reality for most AI teams. Rahman's framework gives us the predictive metrics to know when a model in this environment is actually learning and when it is merely memorizing. Picture 2 hikers ascending adjacent mountain paths. One quickly stops at a false summit. The other climbs relentlessly higher. From a distance, a snapshot might show both of them gaining altitude, but only the one executing the long, sustained climb is actually learning the terrain. Looking at this chart, we can map that analogy to the saturation step, or KSAT. Operationally, it is the earliest training update where the reward approaches its run-specific maximum. Transferable learning occurs almost entirely in the pre-saturation phase. The data in Table 1 proves this. A math-specialized 1.5 billion parameter model reaches its saturation step at update 302. A generic 3 billion parameter instruct baseline saturates at update 55. The smaller, specialized model remains in the active learning regime nearly 6 times longer than the baseline twice its size. Merely increasing parameter count does not guarantee generalization. Generalization is determined entirely by how long a base model can extract signal from sparse data before it begins to overfit. Consider 2 students who submit identical final answers but show entirely different work. One relies on a structured, sequential logic formula. The other writes a jumbled mess that somehow ends with the correct number. A pure grading rubric assigns both of them a perfect score. Computationally, however, the mechanisms they use to arrive at that score share nothing in common. This is where we define faithfulness. A reasoning trace is faithful only if it logically supports and justifies the final answer. It is not enough for the text to simply precede the number. The empirical data reveals a counterintuitive fact. Raw semantic diversity in a model's outputs does not correlate with generalization. In these tests, failing llama models stayed more diverse than succeeding Quen models. To actually learn, a model must generate faithful diversity. Unfaithful traces sever the logical connection between the reasoning steps and the reward, completely breaking the reinforcement loop. You cannot apply RLVR blindly. It requires preparation. You have to show a student worked examples and step-by-step reasoning before you hand them a scored test. This 2x2 grid maps an ablation study designed to fix the failing llama baseline. It tests the base model against continual pretraining, or CPT, on math tokens. It also contrasts non-thinking SFT, which trains only on final solutions, against thinking SFT, which explicitly trains on long-form reasoning traces. Because these runs used identical amounts of compute, the performance difference was driven entirely by the type of supervision, not the volume of resources. The result is clear. Explicit reasoning trace supervision serves as the required ignition for weak supervision RL, while domain-aligned continual pretraining acts as the accelerator. When you attempt to train without ground truth, you face the proxy reward problem. It's the equivalent of a student grading their own test to determine if they pass the class. Over time, the grade and actual knowledge drift completely apart. Self-supervised proxy rewards, such as self-certainty, fail almost uniformly across all tests. This graph tracks majority vote proxy rewards. Quen 3b achieves temporary gains, but hits a terminal collapse at step 500. The Llama 3b data is catastrophic. It hacks its reward score to a perfect 1.0, while actual benchmark accuracy crashes from 45 down to 4. If you were only monitoring training loss, you would assume the model was succeeding perfectly, right up until it became completely useless. Unchecked optimization pressure forces a model to learn obfuscation instead of reasoning. Weak supervision RLVR is not a single lever you can pull. It is a fragile, multi-step chain. The required sequence relies on the 4 distinct nodes: domain-relevant priors, behaviorally faithful traces, extended pre-saturation climbing, and verifiable external rewards. And there is a strict prerequisite. Weaker base models absolutely must undergo reasoning trace supervision and continual pre-training first. Removing any single link collapses the saturation step. The model immediately stops learning the task and shifts entirely to memorizing the reward. Subscribe to Bearded AI Guy for more rigorous breakdowns, and leave a comment telling me which mechanism we should deep dive next: proxy collapse, faithfulness, or the pre-RL recipe. The foundational research regarding these real-world weak supervision conditions comes from the Human Architects AI Agents in Action series. The next time you see a smoothly climbing training curve, remember this: the curve is not the learning, the saturation step is.